Section 1.8 is on continuity. There's a lot of detail in here, but there's a couple of basic ideas that are the main things to remember. So here's the key idea. A continuous function is a function that actually gets to its limit. It gets to what it's headed towards. Okay, so here's a bunch of pictures of functions. We've got 4 examples, and we're going to look at each of them in turn. So the first example, the one on the left, if I look at what happens as x approaches a, the limit of the function is L. Okay, this is like we started off with when we started talking about limits. But if I look at actually what happens at a, f of a is also equal to L. When you plug in x equals a, you get L. When you plug in x is close to a, you get close to L. So both the limit and the value of the function are L. That means the limit as x approaches a is equal to the value at a. And that means the function is continuous. It's headed towards L and it actually gets there. It's continuous at x equals a. In the next example, again we have the limit is L, right? As x heads towards a, the y values head towards L. But in this case, it doesn't get to L. F of a is not L. In fact, f of a is undefined. So we don't get the limit equals the value, and that means f of x is not continuous at a. And just because we're weird like this, usually we don't say not continuous, we say discontinuous. Means the same thing. Okay, here's another example. In this example, the limit actually doesn't exist because the limit from the left is one value and the limit from the right is another value. They don't match, so the limit as a whole doesn't exist. So it's not even heading anywhere, so it can't get there. So this is another way the function can be discontinuous. And finally, here we have a limit. It's infinity, but it could be anything. But it doesn't match the value of the function. Both the limit and the value exist, but they're not equal. That makes the function discontinuous at that point. Okay, so lots of different ways to be discontinuous. Only one way to be continuous, that is, when the limit of the function as x approaches a equals the value of the function at x equals a, that means the function is continuous at a, and that's the definition of continuity. That requires the limit to exist, the function to exist at that point, and those two things to be equal. There's a slightly different thing I want to talk about now in this third example. Here the limit didn't exist, but the limit from the left, and the limit from the right, but in particular the limit from the left does exist as x approaches a from the left. Okay? And the value of the function at a is also equal to that number, L. So the limit from the left equals L, the value of the function equals L. So the limit from the left equals the value of the function, and that makes it not continuous, but continuous from the left. So as you come from the left, you look continuous. It's only when you go past a that something weird happens. Okay. In the same way, you can have functions that are continuous from the right. This one isn't, because even though the limit from the right exists, it doesn't equal the value f of a. The value of f of a is up there, attached to the left-hand branch, not the right-hand branch. Okay. The nice thing about continuous functions is that, oh wait, that's not yet, sorry. I told you what continuous at a point means. Now we have continuous on an interval. That just means it's continuous at every point in that interval. Although, if the point is an endpoint of the interval, then the function doesn't need to be completely continuous at those endpoints. It only needs to be continuous from the right or from the left, depending on whether the endpoint is a left endpoint or a right endpoint. Okay, so continuous on an interval means everywhere inside the interval you're completely continuous, and if you've got a left endpoint you have to be continuous from the right, and if you've got a right endpoint you have to be continuous from the left. So here's a weird function. It's got some strange things happening, and I want to know what intervals this thing is continuous on. I'll put some labels on my axis here. Notice I don't care about the y values. as far as telling me what intervals I'm continuous on. The intervals refer only to the x values. Okay, this thing is continuous on the following intervals. Well, it's continuous from forever to the left up until you hit 1. And it's actually continuous at 1, because as you come along headed towards 1, you get to where you're heading. It's also continuous between 1 and 3, but not at 1, because you don't actually get where you're heading at 1 from the right, and not at 3, because you don't get anywhere, you shoot up to infinity. And it's continuous from 3 to infinity, not including 3 again, because it's not continuous from the right at 3. Okay, again, that first interval includes 1, because the function is continuous from the left at 1. But the second interval does not include 1, because the function is not continuous from the right at 1. Okay, here's what I was going to say before. If the function is continuous at a, you can find a limit just by plugging in a. So find f of a instead of having to deal with finding the limit. So the nice thing about continuous functions is that they have the direct substitution property, which we talked about, I think, in section 5 or 6. Another nice thing is that lots and lots of functions we know about are continuous everywhere in their domains. For example, polynomial functions, rational functions, root functions, trig functions. That's theorem 7 in the book if you want to look at the details. Another nice thing is that you can combine continuous functions. If you have two continuous functions, most of the ways you can think of combining them will produce another continuous function. So adding them, subtracting them, multiplying them, dividing them, or composing them. When you divide, you have to be careful that you're not dividing by 0. But all of those things will give you continuous functions, assuming f and g were continuous to begin with. Again, look in the book for details of these theorems. Finally, one thing that continuous functions let you do is apply the intermediate value theorem. Here is the formal statement of the intermediate value theorem. If f is continuous on the closed interval from a to b, and n is any number between f of a and f of b, then there's some x value c in between a and b such that f of c equals n. Great. All this means is that f can't skip over any y values as it's going from f of a to f of b. So here's the picture. I have a continuous function, and in particular it's continuous between a and b and at those endpoints. Okay, so it's continuous between a and b. I look at f of a and f of b. Those are some y values. And now I get to pick any number n in between f of a and f of b. So I pick any y value in between there. There's one. Okay. What the theorem tells me is that there's some c, some x value between a and b, where f of that c is n. So I can't skip over the y value n. It has to actually hit that y value. And when it hits that y value, you get an associated x value c. That c has to exist. That's what the intermediate value theorem tells you. This sounds kind of obvious, but there's actually some nice applications. Here's just one simple one. Let's say I have this polynomial. Okay. I want to know, first of all, notice that this polynomial is continuous. It's a polynomial, so it's continuous everywhere, any interval I care about. Okay. I want to know, where's there a root of this polynomial? Okay, I'm not going to look for the exact value of a root. That could be really hard, but I'd just like to know a general vicinity where I could find a root. Remember that a root is a place where the function actually equals 0, so I'm solving f of x equals 0. I want to notice a couple of things. If I plug in 1 to this function, I get -1, and if I plug in 2, I get 12. Okay, that's not that exciting, but 0 is in between -1 and 12. So if I pick n equals 0, it's between f of 1 and f of 2. So I'm thinking of 1 as a and 2 as b from the theorem. So I pick a value that's between f of 1 and f of 2. I'm picking the value 0 because that's what I'm interested in, zeros or roots of the function. And then the intermediate value theorem tells me that for this value I picked between f of 1 and f of 2, there has to be some c between 1 and 2 that gives me f of c equals n, f of c equals 0. So I found a root. I found that there is a root somewhere between x equals 1 and x equals 2. X equals c is that root. Okay, so that's an application of the intermediate value theorem. You can look in the book and the exercises for more. All right, that's it. See you in class.